My name is Jon maddog. I'm very happy to be here, and I have a variety of jobs. I'm the executive director of Linux International. That and 200,000 pesos will get you a cup of coffee almost any place. I'm also the chairman of the board of directors for the Linux Professional Institute that does certification for Linux professionals. About that later. I'm the president of Project Kawan, which is a project to make computers more efficient, to make them less wasteful, and to also create jobs for university students so they can afford university. And finally, as of July of last year, I'm the chief executive officer of a company called Optin, which makes peer-to-peer cloud software. And we'll see a little bit more about that later on too. So first of all, I'm going to put in a plug for sysarmy.com, and Ariel, who's a good friend of mine. And when I come here to Argentina, they take care of me and make sure I have enough beer, which last night they did a very good job at. And as systems administrators and computer professionals, I'm sure that people understand that computers can actually be fun. I wish I knew how to do that. Maybe you can teach me. So exactly who am I? Well, next year I will have been working with computers for 1/2 century. Doesn't that sound impressive? That sounds even more impressive than 50 years, right? Half century. And of course, computers are different when I started using them 50 years ago. But since 1980, I've been working exclusively with Unix. In fact, I've never really used Microsoft Windows or anything from Apple. I'm not Richard Stallman. I don't make a big thing about this. It's just that Unix could do everything I wanted to, so why should I bother with this other? And then in 1994, I met Linus Torvalds for the first time, and I saw Linux, and I said, this is the best thing since sliced bread. I've worked for a large variety of companies, most notably Aetna Life and Casualty, the world's largest multi-line insurance company, Bell Laboratories for a while, Digital Equipment Corporation, and a variety of others. And I point out that I worked for very large companies, very small companies, in a variety of different jobs. And I'm happy to say that because of computer science, I've never had a single day with my job. I consider boredom the absolute worst thing that can happen to you. But every day when you go with a challenge, something to do, and you do it, then that's what this really makes work worthwhile. And system design and compiler theory at the university level. One more thing. I am pragmatic. Like I said before, I'm not religious about things. Believe me, I'm not religious. And so I believe in using the best tool for the job. It's just that my feeling is that open source is one of the key elements of finding that best tool. So in May of 1994, I helped to fund Linus Torvalds to come to the United States to an organizational meeting called DECUS, the Digital Equipment Corporation User Society. And after I saw Linux, I helped him get an alpha system so he could expand Linux from working on a 32-bit, miserable, crappy Intel processor onto a 64-bit microprocessor that was known as the fastest microprocessor in the world for 8 years, the Alpha. And the Alpha was a beautiful architecture. If you ask Linus today, he will still say it's a beautiful architecture. And then I helped to assemble a DEC engineering team to help with the port and the local things. And I began to understand the power of the open source community because they did something that was really remarkable. In 9 months, without meeting people face to face, they brought the Linux kernel from 32-bit to 64 Red Hat the distribution of Alpha Linux. The only time I had ever seen a port done that fast was by a well-trained group of engineers who were working together, and I was very impressed. In 1995, I became the executive director of Linux International, a group of companies who saw that Linux had commercial value. It wasn't just a hacker's toy. It wasn't just a technical thing. It could be it could be used for commercial style. And actually it went beyond our wildest dreams. We helped to defend the Linux trademark from an idiot in Boston who wanted to hold it for ransom. We created the Linux Professional Institute to certify Linux professionals with the goal that you could train, you could get your knowledge any way you wanted to, but then you could take this simple test. Well, not simple. You could take this test to get your certification and help to prove that you knew what you were talking about. We also created the Linux Standard Base Project, which creates a set of binary interfaces to allow people to create applications to work across Linux distributions. And all that continue today. And then I've been spending the last few years promoting Linux and open source worldwide by traveling around to different conferences and speaking to people and to companies like yours and to universities. This I do on a volunteer basis. I do not get paid money, traveling expenses, but I don't get paid for coming here because I feel this is my contribution to the open source community. So Latin America, I come from a strange country, and we think of Latin America, we think of it a strange way. You know, we think of the Brazilian rainforest or the Amazon River. Argentina is some type of dance. We don't know. We're not sure. and we really don't. You know, it's really horrible. It is horrible the way that we don't think of Latin America. And when I started coming here, I found out something that I've actually discovered in countries I've been to around the world. That yes, there are rainforests and there are little villages and things, but there's also capital cities that are much like any other capital city, with a lot of people working together, living together, means of transportation and things like that. And when I went to Brazil in 1996, I saw my first Beowulf supercomputer. Now this was only 2 years after the people invented the concept. I went to Sao Paulo and I saw amazing things. It was at the University of Sao Paulo, 100,000 students, 16,000 PhDs in one university of the federal university system. And I said, I need to expand on this. I've started several projects in that time. Project Kala is one of them. Caninos Locos is another project, which I'll tell you about today. A project to stimulate the design and manufacture of small computers inside of Latin America. And in 2018, all the projects are coming together in what I call the Grand Slam. And we'll talk more about that. So in 1999, I helped to start the Linux Professional Institute. We saw a need for commercial people to have well-trained professionals. And a lot of times these people were bankers that could barely say the word Linux. Is it Linux? Is it Linux? What is it? Well, actually it was invented by Linus Torvalds. That's how you say his name. And so he actually calls it Linux. But nobody in the United States could say Linux. So it was Linux or Linux or something like that. And Linus finally said, I don't care what you call it as long as you use it. So we started the Linux Professional Institute, and I became the board chair in July of 2015. In July of last year, I became the chief executive officer of Opt-in. And I believe that Opt-in, makers of open source peer-to-peer cloud software, is going to create a revolution inside of the open source community. We'll talk more about that. Now, who are you? You're entrepreneurs. You're programmers. You're systems administrators. You're the future of Latin America. You are the ones who are going to make your country go forward. And with open source, leapfrog what other countries have had and build up. You don't have to make the mistakes that we made in the past. You are free to go forward fast. And I think that that is the greatest value of open source. Now, this talk is about performance. I've been in the computer industry for 50 years. And a few years ago, I was talking with a friend of mine who has a TV show about technology. And I was on his show, he made the mistake of turning to me and saying, you know, CPUs these days are really fast enough. And I burst into laughter. I said, I've been hearing that for 30 years. Oh man, you see a CPU, it's really fast, it's fast enough. I'm sorry. The CPUs will not be fast enough until I can talk to my computer like I'm talking to you, and it will understand me at least as well as you do. Maybe computers will be fast enough then. But it's not that, you know, why do I say the computer's not fast enough? It's because we're always trying to solve bigger problems. Right? The fastest computers in the world today, the 500 fastest computers, are hundreds of thousands of cores. And they work with petabytes, multiple petabytes of data. You know, and we're still finding problems that we can't solve. So CPUs will never be fast enough. Another thing I hear as I go to universities and their students, Java is the only language we need. Really? My nuclear power plant is melting, and the program that's going to stop it is Java. Well, just kiss your butt goodbye, right? Because in the middle of all this, Java says, oh, I have to do garbage collection. Little piece of garbage here, little piece of garbage there. What was it? Oh, yeah, nuclear power plant. Oh, what happened? It's gone. No. If it's a nuclear power plant, I'm going to write it in C, thank you. And I'm going to have control over everything. But nobody codes in assembler language anymore. Well, God bless. I don't want you to code in assembler language. Okay, maybe 5 or 6 lines of assembler language to make your thing go really fast. But assembler language, by its very definition, means that your code is not portable. And so you should use it with real discretion. However, there's another use to knowing assembler language. And that's figuring out whether or not your compiler is actually generating the right code or generating efficient code. And that's a reason to learn assembler language. Oh, bad dog. Virtual machines make it so you don't have to know that information anymore. You don't have to know about cache and disk drives and latency and things, because virtual systems hide all that from you. Pardon me, I think you're thinking about emulators, number one. Virtual machines typically allow the instructions to actually execute on the machine itself. And only when you reach a privileged instruction does the virtual machine kick in. So yes, you have to know about caches, and you have to know about instructions, and you have to know about data formats. Yes, you have to know that with virtual machines. So the question really is, how much is your time worth? If you're running a program that takes 40 hours to work, and you can't make your next decision until 40 hours have passed, that's a long time. So when people ask me, do you like programming games? No. I don't even like playing games. Ugo can agree to that. When I think of programming, I think of real programs, at least a petabyte of data, at least 5,000 cores. That's what I like real time. The nuclear power plant is melting. You're trying to decide what the weather is 24 hours in advance. Wait a minute, that's not real time. Yes, it is. Because if you take 48 hours to process the data to tell you what the weather is going to be like 24 hours in advance, it's too late. If you take 24 hours to process the data to tell you what the weather is going to be like in 24 hours, it's too late. Because by the time you process the data, you can stick your hand out the window and find out the same answer. So real time in this case means you process the data fast enough to have a useful answer at the time you need it. When Linus had brought out, I think it was version 2.0 of the kernel, the one that had the big, remember that? I called him up, I said, Linus, you know, we could have a lot more use of the Linux operating system if you had better soft real time. He goes, oh, what do you mean, maddog? Of course we have good soft real time. I said, how can you say that, Linus? He says, well, when I'm playing Quake, the monster has a gun in its hand. It's about to shoot me. I hit the button and I kill the monster. That's real time. I said, Linus, put a real gun in the monster's hand and have it aim at you and figure out that you hit the button and kill it in time. So silence on the phone for about 10 or 15 seconds. And then he says, I see what you mean. And the next release of the kernel, the real time was much better. IBM did a study many years ago, and they said, if a person's using a computer and they ask it a simple question, and they expect to get the answer back really quickly, within a third of a second. If the answer comes back within a third of a second, their mind stays focused on the problem. But the human mind is a funny thing. If it doesn't come back within a third of a second, it starts to wander. Oh my God, look at that person. What would I like to have sex with them? What was I thinking about? Oh, the answer came back, 5 seconds ago. I didn't notice, right? A third of a second. Bing, bing. That's very short. That's, in effect, real time. To keep your mind focused on the subject at hand. Now, when I was starting off with computers, the computer would fill this room, maybe have a quarter megabyte of main memory, cost $2.5. You could actually walk inside of it and measure performance by how fast your program ran. Maybe with all of that hardware, we didn't even use an operating system. We linked the device drivers into the program itself, and then you booted the program, much like an Arduino today. And so we measured it by how fast your program ran, because then we could load the next program. See? But today, we measure performance by how long does the battery last in your cell phone. If it lasts a whole day, this is a well-performing cell phone, right? And you're happy with it. If your battery drains in like a quarter of an hour, you're not happy with it. So the definition of performance changes over time. Google and other cloud providers have 10,000 servers plugged in with electricity. If they can improve the efficiency of the programs by only 10%, that means they save 1,000 of those processors. They save the electricity, they save the heat, they save the air conditioning, they save the floor space. Or looking at it another way, they can put even more capacity onto them. So performance is important for them too. And now we are starting to have some new processors come out that I think are very exciting. Actually, field programmable gate arrays have been out for a very long time. I was programming field programmable gate arrays back in 1970 when I was still at school working for the Western Electric Corporation. Only my field programmable gate array was literally the size of maybe 3 of these rooms and cost $2.5 million. And it had a very small capacity, but we needed it because there was nothing else that could come close to the speed. Digital signal processing chips are a new type of thing, which convert analog to digital and vice versa, right? And these are another type of chip that people should learn how to program. And we'll see more about FPGAs later. This was actually my second computer. You can see one of them at the Computer Museum downtown. It is a PDP-8 computer. It is one of, well, back in those days, almost every computer was a RISC computer, a reduced instruction set computer, because every instruction was built out of discrete transistors or discrete relays or discrete food. There was no integrated circuits. And so the concept of creating microcode for every single instruction, no. You created the simplest instruction set you could and made it run as fast as you could. This had eight different instructions, with one of them being an instruction that could shift right, shift left by some number of bits. It only had one general purpose register, and everything went through that. All of your audio, all of your computation was done with that register. It had a program counter that pointed to the place in memory of the next instruction, and it had a stack pointer that pointed to the top of the program stack. That was it. The machine was so stupid, it couldn't even subtract. If you wanted to subtract, you had to do 2's complement arithmetic and then add them together. And to do that, of course, you had to do a series of steps. And so you had to keep pushing things onto the stack, taking them off. It only had 4,000 12-bit words. And it used, as this input-output device, the ASR33 teletype, which read in and wrote out 5 characters per second. So your 3,000 character program, not 3,000 lines, 3,000 character program would take like 10 minutes to print out on the ASR33 teletype. And it used paper, and the paper was expensive. And so you didn't want it to print out unless it absolutely had to. We didn't have a language-sensitive text editor. We didn't have a full-screen text editor. We didn't have a line text editor. We had a character text editor with an invisible dot. And you had to remember where that dot was in your program. And it was a multi-modal text editor. So you in command mode, input mode. And in command mode, you had this command. 0L dot, that was the command. And it would stop to where the dot was. If you went from where the dot was to the end of the line, it was dot L $sign. To print out the whole line, it was 0L $sign. Okay. And now I am briefly going to work through what it was like to create a program on the PDP-8. First of all, you had 12 switches here, and you had a deposit switch. So first, you would set the address that you wanted in the switches, and then you hit load address. Then you would start to put in your data. You need 17 12 instructions in order to get to the point where you could load in the loader program that was on tape. 17 times. Then you stuck your paper tape in here and you read that in. That usually took about half a minute. And now you have the loader in here. Now you're loading your text editor on paper tape. 5 minutes to read in the text editor. Now you can type in your program. You type in your program. You printed it out to make sure it was right. You then punched your program onto paper tape. 3,000 characters, 10 minutes, punching it onto paper tape. Then the paper tape would rip. Do it again, okay? Now you've got your source code program in your hand. You now put in your assembler. The assembler was a much larger program. 15 minutes to read in the assembler off of paper tape. Your assembler is in memory. Now you're going to assemble your program. You have to make 3 passes of your source code program. Remember, 10 minutes long each pass. First pass, you create your symbol table. At that point, it's punching out your binary tape for your program. So now you've got your binary tape, but guess what? You don't have your program listing because it can't print the binary tape and the program listing, which is in ASCII, at the same time. So another pass to get your symbol table. It's now been like 2 hours just to get your program without the time of typing it in. 2 hours just loading programs and stuff like that to get to the point where you now have your program, your listing, and you can put your program into the memory and you say go, and it immediately goes into a loop, wipes out all of memory, and you have to start all over again. After a while, you learn how to do interactive debugging by single stepping through your program, using the switches and the lights, and reading each one. It's like a symbolic debugger without the symbols. But this was how we did it, and this is very good. And I learned how to program this machine in assembler language by reading a book. I got the book from the digital salesperson, nice thick paperback book. He gave it to me for free. And I learned how to read it because nobody told me that assembler language was hard. It's just another language. And I believe that in order to write really great code, you need to know how the machine works. It's not good enough just to look at a high-level language like Java or some other one. So I'm going to give you some examples from my past where knowing assembler language really helped. The first one was back at the Life and Casualty, where they did a lot of programming in COBOL. Now, I know a lot of people have bad thoughts about COBOL language, but let me tell you something. For business, it was very efficient. And remember, these are machines that may have a 1/4 megabyte memory. They're known as mainframes with a 1/4 megabyte of memory running at 100,000 instructions a second. So you needed to make these things work. And one day, this COBOL programmer came to me and said, I can't figure out what this problem is. I've looked at my code, I just can't figure it out. So I knew COBOL. I didn't like programming in COBOL. I liked programming in assembly language. But I looked at this program and I said, I don't see anything wrong. You've done everything correctly. I said, must be a problem with the compiler. Compiler? I said, yes. The compiler is a program, just like your programs, and just like you, the compiler writer came down on a Monday morning after a long weekend, drinking beer, doing maybe light drugs and stuff like that. Looked at the clock and said, oh my God, I only have 10 minutes to put my changes into the pool. Into the pool. No testing. Why? Testing is for newbies, right? And sure enough, the compiler is going to make a mistake. So we told the compiler to generate the assembler language, and it went down to the assembler language. But there it is. There's the mistake. You can see it. We'll put it in a bug report. Oh my God. I ruined his whole month because he thought it could just depend on the compiler. And these were in the days when computer optimizations were still going on. We didn't really understand them very well. In 1969, when I started programming, there was no such thing as a computer science degree. People who were programmers were physicists who programmed the computers to solve their problems. They were chemists who programmed the computers to solve their problems. They were business people who programmed the computers. There wasn't such a thing as a professional programmer. The person who wrote programs for other people to use. You wrote programs for your own use. And a lot of these people who wrote these programs then didn't know what to do with them, because selling programs is hard. You have to have documentation. You have to provide support. You have to guarantee. You have to listen to other customers. You know, these are things that are not fun, particularly if you're a physicist or a chemist or something like that. So these people would contribute their software to DICUS, the Digital Corporation User Society. And DICUS would publish this big paper catalog of all programs. That catalog cost $15 US, which was a lot of money back in those days. And then you would look through the program and you would through the catalog and you would say, oh, here's a text editor and it works on my PDP-8. I'll buy it. $5. Now, even $5 was a lot of money back in those days, and particularly for a college student, because $5 would buy you 10 pitchers of beer. And you had this choice between a really cool text editor and 10 pitchers of beer. I think you can see what direction I normally went. However, the code you got from DICUS was in effect free software, because these people contributed it expecting that people were going to be able to use it, expecting that people could copies. And so I would go to the school store, buy new paper tape, take it to my trusty ASR 33 teletype, and make copies of it and sell it to my roommates for $1 a copy. And after I sold 10 copies, I made back the money I paid to DICUS, I made back the money I paid for the paper tape, and they actually had a little money left over for more beer. Very handy back in those days. So, you know, copyrights when software did not really appear until 1986 in the United States. Patents when software had also not appeared until around 1990. So in 1968, what I was doing was not only very legal, it was also encouraged by DICUS. And DICUS was not the only one. There was Share from IBM. There was Brainstorm from Novell. All user groups and bulletin boards where you would upload your code and then other people could look at them and pull them down over your 1200 dial-up modem. Even slower than ASR 33. But it was the best we could do. So compiler errors was one of the problems that knowing assembler language helped me fix. In the IBM 360, 370 series, there were 4 instructions, which is the slowest instructions in the whole chain. EBCDIC is a code, like ASCII, for representation of characters. So IBM pushed EBCDIC, and the rest of the world pushed ASCII. 7-bit ASCII first. Kind of bad because no umlaut, no little things that were characters. You guys could not really write anything in 7-bit ASCII. And it took people in the United States, because remember, we're a strange country. It took people in the United States a long time to realize you needed 8 bits for European characters. And then all of a sudden, the Koreans needed something more. And then we realized the Chinese needed something even more, right? And so eventually we came to ISO character sets, thank God. But EBCDIC was one of those character sets, even in the early days, and it took one of these very slow instructions to convert EBCDIC to backdecimal, and then you had to convert backdecimal into binary to use it as an index into an array. One tiny little mistake in your code meant that you stored that number as an EBCDIC number. And if you're using it as an index into your array, every single freaking time the compiler came to use that index, it had to go through that conversion. And then you would increment it by 1 to go on to the next element of your array, and you would have stored it and then go back the other way the 4 slowest instructions in the IBM instruction set every time you accessed an element of your array. And if you didn't know assembler language, you would wonder why your program was running so slow. Cache. People say, oh, memory is so big. We have gigabytes and gigabytes of RAM. Yes, you do. It only costs about $10 a gigabyte these days. But the cache in the processor is still relatively small, maybe a half a megabyte or so. If you can keep a lot of your program in that cache, sometimes your program will run 40 times faster. But when you go outside of that cache, all the way out to real memory, your CPU is sitting there going, I'm waiting, I'm waiting, I'm waiting. Please sped this up. It's so bad. You need to think about that as a programmer. With digital Unix, when we first had it as a server operating system, remember, a server operating system on the Alpha processor, the most fastest microcomputer, it booted in 64 megabytes of memory, not gigabytes, megabytes. And our product manager said, it's too big. Think about that these days. My phone has like gigabytes of RAM, okay? And we're saying in a server system that 64 megabytes was too much because the memory was not $10 a gigabyte. It was like $10,000 a megabyte. And so the engineers worked for an entire year to shrink the operating system, to squeeze down all things, to make the data structure smaller so it could boot and work in 32 megabytes of RAM. And amazingly enough, it ran 7% faster. Why? Because the Alpha had a lot of cache. And we could fit the entire kernel and the shell in that cache at one time. And it just screamed. It was amazing. I had a friend of mine named David Mossberger Chang who helped with the Alpha Linux port. And David had the same reason for it that I did. We wanted to get to a 64-bit virtual address space so we could pull in interesting amounts of data. How big is 64? Did you ever think about it? With 32 bits, you can have 4 billion bytes of data in your virtual address space. But with 64 bits, you can have 4 billion times 4 billion. How big is that? That's a gigabyte per second, every second of the day, for the next 5,386 years. That's so much data that you can store 128 bytes of data for every square millimeter on the surface of the Earth, including all the oceans. That's how big it is. And you say, well, I don't have that much data, Mad Dog, but maybe you're trying to edit The Lord of the Rings. You're trying to process it. With 32 megabytes, 70 millimeter slide, you can barely fit one frame of the movie into the memory. And so when you get to the edge of that frame, if you're trying to do compression or any type of work at the edge of that frame, you have to do what we call edge processing. Save all the stuff from this and apply it to all the next one. But if you have bits, you can bring the entire movie into your virtual address space at one time. And now you don't have to do edge programming. You don't have to store the data from the previous frame into the next one. These are the types of things that make me excited. Take note. One time I had a program that this programmer had written for PDP 1170. The PDP 1170 only had a 64 kilobyte address space. And he wrote this program to sort 1,206 32-byte records. It took 10.5 hours for the computer to sort 1,206 32-byte records. I told the program I could punch those records on the cards, throw them up in the air, and pick them up off the ground faster than his computer could program them or could sort them. So one day I couldn't stand this anymore. I took one of my students aside. I said, I'm going to show you some things, like how to use cache, like how to use memory to speed this up. And the student wrote the program with my design. Instead of taking 10.5 hours, we did the same thing in 3 minutes. Because I understood how the computer worked, and the original programmer did not. Magnetic tapes, don't even get me started. Because there's 2 types of magnetic tapes. There's start-stop magnetic tapes, and then there's streaming tapes, which most people use today, thank God. Start-stop magnetic tapes meant that you had to stop, physically stop the tape drive in between blocks of data, and it started back up again. And so you wanted to make your blocks as big as humanly possible. However, if you made them too big, the reliability of the tape drive meant that maybe it would make a read error halfway through the block and have to go backwards and start again. And if you didn't understand all of this, then on Unix systems in particular, your tape would take hours and hours and hours to write the data onto them. So one day I had this customer come to me and says, I'm exhausted. I can't make the tape go fast. I said, I'm going to tell you a trick. The Unix commands have been changed so that DD does multiple block writing. It does, and it will keep the tape streaming. So all you have to do is put DD in front of whatever you're doing, and it will do all the streaming and keep the tape streaming. And then the next command will just see a stream of data coming in. And the guy looked at me and says, no, it can't be that easy. Yes, it can be that easy. And we purposely did this, and we never told anybody. And so the next day I get this email from him, and all it said was email. It's streaming, right? So today, I actually run into universities that say, we teach students Microsoft Office and Oracle because that's what all the companies use, right? And we need to make sure that our students can go out there and get a good job afterwards. And I say, help me with this. Really. You have a student who you're trained to be a civil engineer, and they can build bridges which aren't supposed to collapse. They can build buildings to hold, lots of things. A chemical engineer is going to be working on compounds. A brain surgeon, doctors, lawyers, all these smart people you're training. And you say to me that they can't pick up a book on Microsoft Office and learn how to use it in a day. Because that's what you're saying. No, that's not what we're saying. Yes, it is. Your students are either smart or they're stupid. If they're smart, they can pick up Microsoft Office in a day. If they're stupid, forget about it. I don't want them operating on my brain. Java and IT or TI or whatever they call it, instead of learning about assembly language and operating systems and how the hardware actually works from the bottom up. Because when you learn something from the bottom up, then nothing is ever opaque to you in the future. You can figure it out. You may not see it down to the very lowest level, but you can think about how it would actually work. Yeah, okay, I understand that. Where somebody says something to you, you say, no, that's complete bullshit. And that's what we should be having. And high school students these days, they get a laptop, and on the laptop, there's this little sticker that says, you open this up and your warranty is full. So they never open it up. And they go and they buy a game and they put it on there and they write some HTML and they say, I am a programmer. No, you're not. I'm sorry. Because this is the way those high school students look at computers. The computer is my friend. No, it's not. It hates you. I was a Unix systems administrator one time, and people said to me that Unix was unfriendly. Really? There was an operating system on the Cyber CDC-70. That was a supercomputer of the day. That operating system was not only unfriendly, it knew humans were out there and it hated them. No, Unix has always been friendly to me because it let me do what I want to do. And in reality, this is how computers work. There's nothing friendly about that. But you have to know all those pipes and think about them as you're doing this. The latest bugs that went out that rocked the whole world, you know, they were bugs that had to do with out-of-order instruction execution. How in the world can you even understand what the problem is if you don't really understand how the computers work? And where can you make the decision about whether you have to run one kernel or another one, depending on the processor type? You could lose 17 to 20% of your performance by running the wrong kernel or the wrong architecture. Now, I talked before about everything and asking. These slides got out of order, so I'm going to skip over these two. But the real life effects of this dumbing down of high school students coming into university means that the university professors have to start a lot simpler, back further, with telling students really what the computers are about. And the university professors who invented the Raspberry Pi in Cambridge, England, said that incoming freshmen today know less about computers than the ones of 20 years ago, who the Amigas and the things that they had to bring down the source code, compile it, and they got these weird statements called syntax errors and all data conversion errors, and they had to figure out what those were. I remember we had magazines that actually had the programs listed in the magazines, and you had to type them in. And you're busy typing them in, and you say compile them or assemble them, and they wouldn't assemble. And you're looking, and you're reading, and you're reading. The next month, there would be a new version of the magazine. I'm sorry, I kind of missed the brand line. 33. But you learned a lot, right? You learned a lot. And they created the Raspberry Pi specifically to fix this problem. They purposely sold it without a case. They purposely made you figure this stuff out. And I think I have to applaud them for what they did. But quite frankly, the Raspberry Pi is boring. It's boring because the first one was a single core system with a 0.5 gigabyte of RAM. And to me, this is a fine system for maybe an elementary or even a high school student. But for university students, it quite frankly sucks. And the reason it sucks is because there's a whole bunch of little computers out there that each have different capabilities. Multi-core systems, which allow you to practice things like symmetrical multiprocessing, race condition issues. You can't have a race condition issue on the kernel level with a single core. That's impossible. But a second core, you can have them, and you will have them, right? So all these little computers have different things, particularly this one. This has two separate processors on it, one core. One runs fairly slowly, but uses only a slight amount of electrical power, and the other one runs a lot faster, but uses a lot more electrical power. And so when your system is lightly loaded, everything works in this processor. And then as your load builds, you can start to schedule other processes in the faster one. Then as it slows down again, you migrate them to the slower processor again. So that's this big little architecture. It's used a lot in cell phones because you want to have a longer battery life on the cell phone. So about 6 years ago, when the Raspberry Pi Foundation created the Raspberry Pi, I happen to know several people on the board. Now I'm going to stop for a second and tell you something about large corporations. A lot of people think that in large corporations, you get things done by writing a business proposal, giving it to your next management, having them look at it, study it, figure out how it fits into the product line, and it goes up until finally they say, oh yeah, we'll fund this or not. And all of this can take a year. This is not what you do. A digital equipment corporation, you pulled in favors. I had worked with them for 16 years, and when the Alpha project came out, I started to pull in my favors. I started to go to people and say, I did this favor for you. You're going to do a favor for me. That's how we got it done. Because if I waited for my management to do it, never happened. So I knew a lot of people in the Raspberry Pi board because I've been in the computer industry a long time. And I called them up and said, come to Brazil, because Brazil has this problem, and so does Argentina. You have a very large import duty on things that maybe you should look at again. But the Brazilian government is pretty stubborn about that. And the Raspberry Pi that costs $35 in the United States costs $150 in Brazil. And these are people who have 2/3 of the purchasing power of the United States citizen. So for them, it's more like $200. And I said, that's just too much. You know, you're not meeting your goal of the Raspberry Pi Foundation. And so for 2 years, we worked with them to see if they would produce the Raspberry Pi in Brazil. And after 2 years, and actually producing 5 Raspberry Pis in Brazil, they came back to me and they said, no. They never told me why no. They just said no. I have a theory. You see, the Raspberry Pi Foundation is in Cambridge, England. That's part of the political group known as the United Kingdom. Currently, they are having their units built in by Sony in Wales. Wales is another element or member of the United Kingdom political unit. And so as long as they're creating Raspberry Pis in Wales, then the British government smiles upon them. Brazil is not a part of the United Kingdom. And so I think you can see my drift here, right? Creating jobs and producing systems in Brazil is not beneficial to the United Kingdom. So I went to another little company in China called LeMaker. And LeMaker was making the Banana Pi and the Banana Pro. They looked a lot like a Raspberry Pi, except they were better. And they only cost $5 more. So you were willing to pay the $5 in order to hook up a SATA drive to your Raspberry Pi. And you got twice as much memory. And I worked with them and I said, would you mind manufacturing this system in Brazil? And they said, no. Okay. And a couple months later, I went to CeBIT, the world's largest computer show in Hanover, Germany. And who was there except LeMaker? And they not only had their Banana Pi and Banana Pro there, but they had a new little system called the Guitar. Very nice little system. This is the specs on it. And I said to them, would you mind manufacturing this in Brazil? And they said, no. So then I took them around and introduced them to people and stuff because I'm a friendly guy. And I like doing favors for people. And I took them out to drink and we had beer. We went to this big German beer hall, bought them food and stuff like that. And they said to me, if you ever come to China, please come to our factory. Unbeknownst to them, I'd already scheduled a trip to China 2 months later. And I went to Shenzhen, went to their factory. We went out to dinner. I talked with their engineers. Everybody was happy. At the end of the dinner, one of the founders turned to me. I said, you told me no. I said, well, that was last week. And we're a small company with limited resources, so we'll do this. Now, it's taken us 3 years to get through all of the logistics, customs issues, stuff like that. But basically, we can produce this system for only $5 US more with all the taxes paid than people in the United States can purchase it. So we're going to be selling these in the next month or two as we and the Raspberry Pi in Brazil at this moment is selling for like $60. The Raspberry Pi that only has 1 gigabyte of RAM, not 2, only USB 2, not USB 3. It works at 40 degrees Celsius, not 70 degrees Celsius. Hugo lives in Rio de Janeiro, and a lot of times in his apartment, it's 40 degrees Celsius, maybe 45. So this works, without a fan in places that the Raspberry Pi could not. It's also much better with ESP support, electrostatic discharge support built into the system. And this is only one of 3 processors that we're developing through a program called Caninas Lucus, is to do Internet of Things. We name all the processors after dogs. I'm Mad Dog. The professor in charge of this is Mad Mutt. And this is the Labrador. And the Labrador friendly dog, it's the first one in our line. We have also a guard dog. It is a router system. We'll see more about this a little bit later. But this is the high end. And then at the very low end, we have a very, very, very tiny computer about the size of the 1 peso coin. And it basically, we call it the flea. We work with the Chihuahua, but nobody likes Chihuahuas. And so we figured that every dog has fleas. That's what we have. It'll run for 2 years off of batteries. And it uses LoRa as a communications device over long distances. And this has become the base of the Brazilian IoT program. We are creating this. They're designed in Brazil. They're manufactured in Brazil. Now, we realize there are other countries around Latin America which have similar programs. What we would like to do is collaborate with them and offer them our manufacturing facilities if they would like to do new designs, and offer them the manufacturing expertise that they actuated. And so why am I showing you all this? Because this is the type of stuff I like to do. I like to create supercomputers that fit in a briefcase so I can take it around and show people. And this particular supercomputer was built with banana. The Labradors, I will change it over to the Labradors. And why is this interesting? Because I can teach high performance computing with this. Carry it around. I can also show high availability computing to make it so that if one of those computers stops working or one disk drive disappears, you still have access to your data. I can do that as homogeneous computing with one operating system, or I can do it as heterogeneous. I can put BSD on there. I can even put Windows 10, although I don't know why I would do that. So it's very portable, very modular. The original cost me $500 US. And by making some cost reduction on it, I want to get it down to around $400 US for this. And it works off of about 20 watts of power. Now, in 2018, that's actually wrong. It'll be 25 years of GNU Linux and version 1.0. And during that time, lots of things have changed. Memories have. But we still need to understand how it works so that we can make proper programming decisions. Beowulf supercomputers occurred or started to occur only in 1994. And so that began 25 years in 2019. GPUs we're not just using for graphics anymore. When I started programming, there were no GPUs. We were doing graphics with the main processor putting pixel into place. Oh my God, was it slow. And even with just black and white, a single plane, bit on, bit off graphics, it was still slow. But then we went to graduated grays, and you needed to have multi-bytes per pixel. Then it really slowed down. And so, we invented GPUs to offload the main CPU and do the graphics better and faster. Before that, there was a similar type of thing. The 386 processor, when it first came out, separate floating point chip, and some of the gentlemen in the room probably remember this. You had to buy a separate floating point chip to put onto the motherboard to give you floating point accelerator. And eventually, so many people were using that Intel just said, we give up, we'll build every chip with floating point. The same thing is true of graphics. Took a long time for people to start using real graphics, but eventually, to have a processor or a system without a decent GPU, nobody would buy it. The same thing is going to be true of field programmable gate arrays. Before, they were multi-million dollars and very big. Now you can buy them for $21 and they fit on a very small section of the board. And as they become more and more common and used for more and more things, they're going to be more and more prevalent in systems, and more people are going to use them. What do we use them for? Encryption, decryption, compression, mining Bitcoins. Because GPUs, so people used to mine Bitcoins using the CPU. That very quickly went out of style. Then they said, let's use GPUs, and they're okay, but they use huge amounts of power because they weren't meant to do that. Their instruction set wasn't meant to do that. They're wasting huge numbers of transistors with huge amounts of electrical power, wasting a lot of it. And so people go from there to ASICs, specially designed circuits that are specially programmed just to do Bitcoin mining. And the only problem with that is when the Bitcoin people change their blockchain and change the algorithm, you have a useless ASIC. Recently, there was a company that generated an ASIC. They had $4 billion worth of ASICs about to release it. And the Bitcoin people changed the algorithm. $4 billion of junk. But with an FPGA, it's almost as fast as an ASIC and almost as efficient. But it's, and you can change it. You can reprogram it if the elements change, if the problem changes. Now, all of these things are very exciting for me because I love programming new technologies. But I'm going to be retiring in 3 years. I'm going to stop traveling around, stop talking like this. People want to hear me, they can come to me instead of me going to them. And this is just the time so I don't have to learn quantum computing. Because somehow having the answer before you write the question is hard for me to understand. So in all of these categories of performance, percentage speed up, memory utilization, cache utilization, power efficiency, there may be more and more categories of performance that we should be thinking about other than just speed and that. And one of these is parallelism, because Moore's law is coming to an end. Even if we can make the pieces smaller and smaller, getting rid of the heat generated by turning up the clock and pushing the electrons through is getting to be harder and harder to do. And so people write multi-cores. You run each core at a slower pace, generates less heat, and you just have more of the cores to do that. But you need to be able to parallelize your code to be able to take advantage of that, unless you want to run all series of different processes in one single thread. That's okay too. And parallelizing your code helps with tightly coupled programming like SMP, or loosely coupled like PPM or MPI, message passing interface, basically the core of the Beowulf system. And also cloud computing. Cloud computing really takes a benefit if you can. Wow. And so a lot of people over the last few years to generate the resources that be able to use them in for a short period of time. Some people are advocating Internet of Things. Join the crowd, join the cloud, and here's the problem. I have these things out here, things all over the place, here in Argentina. They're generating huge amounts of data. I'm going to send all that back to Redmond, Washington, to Microsoft Azure. I'm going to send all that back to Amazon. And these companies say, oh no, we're having data centers here and data centers here. I don't care where they're putting their data. Huge amounts of data to the processing, and then extract just the data you want to send some other place for processing. This is going to be insecure. It is going to be very expensive in transmission. It's going to have huge latencies introduced. And it's just the wrong way of doing it. The way that most people talk about Internet of Things is they have an application which talks to the things, and then the application talks to the cloud. We think a better way is to have everything as part of the cloud. So before, I talked about the address space and the amount of data which you can have in a 64-bit address space. But internet numbers are 128 bits. It's 64 times 64. It's so huge, you can actually give an address to every single neuron, proton, and electron in the entire known universe. That's how big 128 bits is. And so we can have everything have an address. And everything should be able to authenticate who it is and who can connect to it. And so now you can have multiple applications talking to everything, as long as they're authenticated, and they can set up a private virtual network to that thing. And what does this mean? You could actually set up a small cloud of things. And now that cloud of things can have its processing done and send out its processed data to any other portion of the cloud. But the issue here is you have to have control, not the cloud people, not Amazon, not Microsoft, not anybody. So the problem with big cloud versus what we call peer-to-peer is that big cloud is centralized. The entire internet was made to be decentralized. If you have an earthquake, a flood, a hurricane, volcano, some disaster that wipes out a portion of the internet keeps working. If I came to disappear tomorrow, the internet would keep working, right? If the high order DNS server was to disappear, the internet would keep working. And then along came Amazon and ruined the model. They took this distributed, it always works model, and they said, no, we're going to centralize it because we want to make money. Wrong. Okay. And I told you I came from a strange country. Despite the fact we have this image of our Constitution and rights and stuff like that, unfortunately, ever since 9/11 and the Patriot Act with the Cloud Act, we've taken away some of those freedoms. Not necessarily from people like me, because I'm a US citizen, but I hate to tell you something. Under our Constitution, you have no fucking rights at all. And not only that, you have no right to privacy, you have no right to security, you have no right to keep, for my government to look at your data, absolutely no rights. And I came to Brazil to tell them this right after the Patriot Act started. And they kind of listened to me and said, oh, okay. And then Edward Snowden showed them that the NSA was reading Dilma's emails, and they stopped laughing. It's not funny, okay? A lot of people in the United States think that Edward Snowden is some type of villain. I think he's a hero because he woke up a lot of people in the United States about what we're doing. And the other thing about big cloud is they never buy anything from you. They only want to sell you stuff. If you have a solar panel, or if you have a wind, or if you have some type of electrical supply hooked up to the electric grid, the electric company will buy that electricity from you. Cloud vendors don't do that. They don't buy your resources from you. So peer-to-peer allows you to store the data where you want to store it. If you're running a hospital, you decide to store the data, the patient's data in the hospital and never let it outside. You can determine what happens. And you can buy and sell resources from people who have them to sell to you, maybe a lot cheaper than the big cloud providers would sell them to you. You can locally process your IoT things. And you get better control on latency because you're keeping the data low where the processing is going to be. One time, I was in Chicago many years ago. I was with the Red Hat people. They were just starting up. And we were asked to go to talk to this organization called Fermilab. It was outside of Chicago. We had to get in a van, drive out there. Big open field, huge building at one end. And to make a long story short, they were running a collider to look for the sixth quark, the small element of itself. And they had run their collider for an entire year, and they had only seen 12 quarks. Each one existed for only 10 to the -0.2 seconds. So it's hard to see what it looks like. Oh, there's a quark! Gone! So they were increasing their magnets 200 times. They were going to generate 200 times more data. And they could dig up the entire accelerator. They could replace all the magnets. But what they couldn't afford was the 200 times the 200 Spark stations they already had. It was too much money for them. So they switched to Intel Linux. This is control of your costs. So we have invented something called Visitó. It's peer-to-peer open source cloud software where you can create your own cloud. And if you have a number of computers inside of your building, you can create your cloud, and then you can run your applications in that cloud yourself. If you want to match this up with big cloud services and put some of your things there and use Visitó for some of them, that's fine too. You can do that. You can even run Visitó on top of the big cloud. Why would you want to do that? Because Visitó encrypts everything, right? We have very strong authentication, very strong encryption. It makes it very difficult for certain organizations to spy on you. We also have this thing called the Visitó. And this is free open source software. You don't even have to have hardware. We also have this software called the Visitó Bazaar. It's like Android workspace, the Android market, the Apple market. And you can buy and sell resources using this little token called Goodwill. And then we have the Visitó blockchain router. This is version 1.0 of it. We've redesigned 2.0 to be much more powerful, and we'll be producing that in Q3 of this year. It is not only a broadband router that does wired or wireless routing, it's also a RAID-based NAS device. So you can set up a NAS server with RAID 0 to 10. It has hardware processors on board which you program to offload the main CPU from doing RAID. It is an IoT gateway. You can put an Arduino shield on it or run GPIO pins. And so if you develop some IoT thing with the Raspberry Pi or with the Arduino, the router then drive it. We do a lot of security on it. We have a trusted system that checks each packet going in and out of the router to see if there's viruses in it. We use a fuzzy logic that was developed by Albert Aho, one of the authors of the AUK program. And finally, we do green cryptocurrency mining. In addition to all the things I talked about, the system uses only 18 watts. And you can do cryptocurrency mining with the same 18 watts, as opposed to a GPU a minimum of 350 watts to 400 watts of power. And we create a hardware wallet we can store your cryptocurrency in. We're also bringing out a coin called Con, which, by the way, when you say it, you can't just say Con. You have to say it, Con! It's Con! Okay? And that's going to allow you to purchase things. It is a utility token. It is not an investment token. We don't expect a Con is going to double, triple, quadruple in price or whatever. We wanted to make it so that you can buy things and sell things easily over the internet. And therefore, we can create what we call economy operators, people who make an economy out of the services that they sell. So, side effects of studying performance: you can learn some really cool assembly language. You can learn to write your code better and faster. After a while, it becomes almost automatic. How should I store this piece of data? Oh, don't store it in lipstick. Oh, God, help. Convert your data at the very beginning, and then use the most efficient form throughout. You can create an open source portfolio of the work you've done and show it to people. And I try and encourage university levels courses in this. So in the summary, I recommend to people that you learn some assembly language. People come up to me and they say, what's the first language I should learn? Kind of visual and everything. But if you are a Unix or Linux person, you know, teenage years or above, the first language you should learn is Bash, because Bash is always there. You never have to download some new library or anything. And it's very efficient, and you learn the process of flow and stuff. Second language, these days I recommend Python. Some people don't like it. I do. The third language, assembly language. Because if you go on, if you learn how to program in C, C is a lot easier to learn when you already know about registers. And you know what dereferencing a register is. And you know what happens when that dereferenced address is 0. Okay, inadvertently. And it's all easier to understand if you've had assembly language. But if you haven't, if the only language you had was COBOL, which has none of these features, then it's harder to understand. And then after that, C, C++, learn multiple languages, because sooner or later you'll be put into a situation where you have to help maintain some code that other people have written, and you want to make your code better. This is crappy. So it all looks like it was written by one person. So when you go away, they maintain your code. And that's about it. Here's some resources I've had over the years. Really look at GCC, really understand the different flags for optimization that it does and how all of them work together. And we are up debugging with that. Very good book, even in 2008, it's still viable. Grind is interesting free software that you can make your programs run faster. And then if you're interested in ARM assembly language, you can get the ARM assembly language reference manual. Now these days, I would recommend taking a look at RISC-V or RISC-V. It's a new architecture coming out. Absolutely no licensing that has to go with it. You can just use it. And there's going to be people making processors from the very, very tiny processors up to server systems with 64-bit, even 120-bit address spaces. So it's worthwhile to look at that and start to see how that goes. Maybe join in some of the projects that they're doing. With that, I'll try and take some questions, comments, or ideas. Because I've been talking a long time, and my coffee's cold, but I can still drink it.
Just quick question. Are you even vaguely aware of the CIA project from here, Argentina, CIA?
No, I'm afraid not, no.
Okay, it's kind of similar to the Caninos Locos thing, but it's made by a bunch of electrical engineers. So the middle line is for industrial. It's basically an open computer for industrial usage. And I'm very fairly related to that. They've had a bunch of problems getting that manufactured, produced, imported. Seems like they would benefit and could share things with the Caninos Locos people.
Happy to do that. Right. So when Google was inventing Android, they said we want to have an open system with source code, and it received a lot of flack from people that they'd chosen certain partners to bring it out quickly because they saw what Apple was doing. And, you know, so it was a closed project that eventually they wanted to make it open. And we're doing the same thing with Caninos Locos. The first design is not a completely open design. It has some issues, some binary blocks, but we're going to get it out the door. We're going to make people, you know, excited about the program. And then the next version, we open it up for more input from different parties, people who want the things we need, as we work toward a completely open system. Professor Zufo and I are both committed to having it completely open and no binary blobs in it, that people can manufacture the computer themselves, the processor themselves, with an open fab, okay? So they can check to make sure that nobody's building backdoors into it. I am both the most paranoid person on earth or the least paranoid person on earth, depending on how you look at it. Maybe Richard Stallman's more paranoid than I am. But we have reason to be. And we know not only what can be done, but what has been done. And it is terrifying, the steps to which my government has taken to extract information. They have taken shipments of processors going from the manufacturer towards the end user, intercepted them, unwrapped them, substituted ROMs in them, wrapped them back up, and sent them on so that nobody could detect that they've been tampered with, yet they could easily break into them anytime they wanted to. During Desert Storm, people were amazed that the missiles that the United States had could fly right through the window of some of the Assange's government offices. What they didn't know was the Hewlett-Packard printers that those offices had purchased sometime before was giving out a signal which told them exactly where they were. And that's why we can make the missiles fly right to their office. It's just amazing. And again, even though people say, well, I think I'm storing my data here, the nature of the internet means it may be routed some other place. And it's one specific place where it's routed as you go between the United States and Europe that the NSA is listening to every packet. And if you think this is not possible, they are doing it. And it's not the concern they can't break your encryption. They can break your encryption. It's just, can they break it fast enough? Is it in real time? And the less that's encrypted, the easier their job is. So please, encrypt everything. Everything. Your child's lunch menu, mail to anybody. Encrypt it so they won't know what to decrypt. That's the beauty of it. If we encrypt everything, they will know what to decrypt. And then people say, oh, Mad Dog, you're on the side of child pornography and you're on the side of terrorists. And no, I'm on the side of the founding fathers of the United States who were tired of having the British government barge into their houses without a subpoena, without a search warrant, and just take anything they wanted to. And so they wrote into our Constitution that this was illegal. And now my government is breaking that Constitution in the name of terrorism. If you think that somebody's a terrorist, it's you go to a court, you provide the evidence that you think they're a terrorist, you get that search warrant, you go to that person and you say, hi, either you decrypt what you've got or you go to jail. So they either go to jail because they don't decrypt it or they go to jail because they do decrypt it. But the thing is, you knew about that from some other means other than searching their property and their person without their permission. That's what I want. And I'm tired of my government trampling over my rights and my protections with the word terrorism, because they're more of a terrorist than any terrorist I know of. Okay. Next question. Oh, thank you. I'm actually still drinking my cold coffee.
But you told us a lot about the history of computer. I want to know how do you think the future of computer is going to be now that most of devices are cloud except from Linux and people is getting to know about the devices they use.
So first of all, there's some very interesting technologies that are coming down the pipe. One of them, to give you an example, something called resistive memory. So today, if we have a memory cell, it's typically made up of a couple of very small transistors that go into a flip-flop. And then the flip-flop goes into what's known as a half adder. So this takes not only maybe 5 or 6 active components to make, and when you turn off the power, it forgets what it was doing. So it's volatile memory. RAM is volatile memory. There's this thing called resistive memory that's actually made with a single atom. And you change it into an ion. And the placement of the ion in the material, and when you turn off the power, it still remembers. Its access time is approximately twice that of normal RAM. So it's extremely fast and extremely dense. And you can estimated to hold all of human knowledge in something the size of my fist. And you say that's impossible, Mad Dog. I will remind you that you have a computer with some storage firmly between your ears that has that type of storage capacity. It's made up of neurons and synapses. And the length of your synapses, if they're put end to end, would go around the Earth several times. So this is a type of technology that's interesting to me, because then we could really have, and because it's non-volatile, if we can produce this in an economic way, then overnight disk drives disappear. No disk drive could possibly compete with this. Flash drives would disappear because flash drives couldn't compete with it. Everything would become this technology or some of it. This would be very exciting. And Hewlett-Packard was actually working on changes to the operating system of Linux, new file systems, with even the question of, do we have file systems anymore? Or do we just have a big heap inside of this because the processors are fast enough to go through and find anything we want? This is the type of stuff that's very exciting, right? And when they do, it's going to be pretty fantastic. So that's one aspect of it. And then the other aspect we had the other night at Campus Party was a discussion of artificial intelligence. I love when people talk about artificial intelligence because they say somehow they don't understand what the intelligence part means. They understand the artificial, maybe. It's not carbon, oxygen, hydrogen, nitrogen, you know. It's not organic. it's maybe inorganic, but it could be organic, just artificial. And, but the intelligence part is what screws them up. They think that if you write a program to tell something to do something, that's somehow artificial intelligence, no matter how good it is. Maybe there's expert systems that are written that way, but that's not artificial intelligence. Artificial intelligence means it can learn on its own, right? And it can go through generations of artificial intelligence in a matter of an hour, whereas we go through a generation of intelligence. 30 years. You and your wife get together, you have a child, and maybe it's more intelligent. We find out in 30 years. But artificial intelligence could do it very quickly. Alan Turing, one of my heroes for many reasons, in 1939 realized that the human mind was made up of neurons and synapses. And he said to himself, if we gave a machine enough memory and gave enough time, could it really be intelligent? Now, I'm an atheist. I'll tell you that. I don't believe in God. Therefore, I don't believe in a divine spark of difference between the human being and animals. I believe in evolution of it, that your mind evolved better and developed the capabilities of intelligence. Therefore, I have no problem in imagining a machine being the same way, that it could go and become complex enough and be able to do it with the same chemical, electrical characteristics of the human mind. So yes, I believe that someday we will have machines as intelligent as we are. And I'll be able to talk with them like I talk with you. And they will understand me the same way you understand me. Okay. Now, what does that mean for society? We talk about autonomous cars. Cars that can drive themselves. And everybody says, oh yeah. And they recognize the fact that taxi drivers will be obsolete. Uber drivers will be obsolete. Truck drivers will be obsolete. And these cars will drive themselves. And people say, well, I like driving my car. I want to drive my car. The very moment that insurance companies realize that autonomous vehicles are safer than human beings, they don't have to be completely safe. They can still have accidents, but human beings are terrible at driving. In the United States, we kill 40,000 people a year because people are texting and doing other strange things, drinking coffee and doing other strange things when they're driving, falling asleep. And insurance companies, when they realize that these machines are better at driving, they will raise your insurance rates to the point that you won't be able to afford to drive. And if you're found driving without insurance, the court will rip you. And so people will stop driving unless you're very, very rich and you have your own private racetrack that you can go on. And what does this mean? This means that in cities where we give up huge amounts of space for cars to be parked, they disappear. Because you'll just, with your app, you'll say, I want to go from here to there, and the car will appear in a matter of minutes, not seconds, not even minutes like Uber, seconds. And you'll step into it, and it will take you to where you're going, and it'll drop you off, and it'll go on to the next person. What does this mean? We save a lot of space in cities that are tied over to parking spaces and stuff like that. They all disappear. The number of cars we need to manufacture drops to 1/10 of what they are. Because the cars are now always going around that never park. So we need lots less of them to transport us. What does that mean? Well, there's a lot less steel needed and stuff like that. It affects the entire ecosystem. A lot of people haven't thought that far. People say, oh, I can, all these jobs will be wiped out. Well, just retrain these jobs, these people, to do other things. Really? This is going to sound very egotistical, but I'm willing to bet that every single person in this room has an intelligence quotient above average. IQ of 100 is average. It's not high, it's not low, it's average. And you people, I think, are all above average. That's why you're in this room. It sounds egotistical, but there's also a lot of people below average. And they struggle to do jobs that we would find easy. What are these people going to do? They can't be retrained to be a brain surgeon. They don't have the capability of learning that. And that's where you have these people talk about guaranteed income. Oh yeah, everybody's going to have a guaranteed income. They will be able to live their life. But you know, the rich people always have a problem with that. They always have a problem with saying, oh, we're going to pay people just so they can live. They don't even want to give health. In my country, they don't even want to give health care to people so they can do a better job. They don't want to supply a free education to people so they can get a better job. And we expect them to be able to give their money to people that aren't working? They've already said they're not going to do that. And there's going to be a war like we have never seen before. There's going to be a revolution. Because when you say to somebody, I'm sorry, we're taking away the job, we're taking away the only thing you do, I'm replacing you with a robot. And people are stuck with nothing they can do, no way to earn money. They're going to revolt. It's going to make the French Revolution look like nothing. And people say to me, well, should we fight artificial intelligence? I say, you can't fight it. Because you can do artificial intelligence with a Raspberry Pi in a locked room and nobody will ever know you're doing it. And someday that will escape. And I hope that it likes me. I hope that it keeps me at least as a pet. I love science fiction. I used to read science fiction, and I thought about this great science fiction story. I want to publish it someday. This alien comes down from outer space, visits the Earth, and finds out there's only silicon-based life forms, robots, and stuff like that. There's no organic life form left. We killed it off many eons ago. And the life form says to the silicon life form, were there ever organic life forms? No, we don't think so. Oh, well, then do you have a religion? Oh, yes, we have a religion. There was a God. There is a God. And we have his book in our cave. And so you go to the cave, and inside this glass case is the book that tells the silicon-based life form all about artificial life. And you start to read it, you realize it's Alan Turing's 1939 report on artificial intelligence. So, I hope that they like me. I'd be perfectly happy to be their pet as long as they give me really good beer. Any other questions?
I have Rafa.
Hi. Will you, regarding what you said earlier about learning first Bash and then Python and then probably assembly language, for example, would you still recommend this for people outside that we want to, for example, bring closer to the world of programming?
No, not really. I think the thing, people outside of programming and stuff, what they should do is write some program so they realize how stupid the computer is and how much it takes to do even the simplest things. And so they should be able to talk to a programmer, and a programmer should be able to, they should be able to understand how to talk to the programmer. They should understand that what they're asking of the programmer isn't simple. It's going to take maybe a couple hours. Or is it complex? And it's going to take a couple years. They should have that level of understanding. But to make each person learn to that level I can understand when my doctor's telling me I'm having a heart attack, and I know a little bit about it, but I'm not going to do the operation, even if I could. No.
Thank you.
Sure.
Okay, so last year I celebrated my 4th century working on IT. And a topic that interests me is aging in IT. I'm wondering how do you do to keep engaged? Something that I'm every time is how to keep engaged. Or I'm engaged, but I don't think that's something that everybody in this industry can do.
Well, first of all, there's typically 2 paths you go, where you stay technical and you keep reading magazines and you keep, looking on the internet and seeing what new things are coming along and trying to apply that to whatever you're doing. So, and then some people completely jump. So I had a friend of mine who worked in digital. He was really, really expert on security. But after a while, he got tired of it, right? Telling people the same things. Don't put your password up on the screen, stuff like that. So he got interested in Apache web server and joined the Apache group just to fix bugs. He would look at the bug list, say, oh, there's a bug, I can fix that. He would fix it. And after a while, the Apache people liked what he was doing. And they said, hey, we'd like you to write some extensions to what we're doing. So he would write them. Would you like to come on to the core team developing the Apache web server? And he did that, and then after a while, IBM came to him and said, we'd like you to work for us, work on the Apache web server because of all you're doing, and we'll pay you full-time salary to work on the Apache web server. So he's done that, he's been doing that ever since. So he transitioned from doing security to doing the Apache web server. And people can, do that. I have a slightly different path. I started off as a programmer, systems administrator, but over time, I realized that I had a gift of taking complex technical things and explaining to them in a relatively simple term to people who need to know. And likewise, I could take people's needs and explain it to engineers in terms that they can understand, and the business terms around them. Because I feel that engineers understand something about the business, right? And so I went that path. I still like technology, still like working with technology. And I can understand large segments of the technology just, again, because people explain what it is. I can see in my mind how it can be done and understand its benefit. But, if somebody said to me, let's write a highly distributed Beowulf program to do this, it might take me a little while to really get back into that again. But I do understand it. I know how to do it. So there's a different paths. And the wonderful thing about computer programming, data processing, computer science, computer engineering, is there's so much to learn, so many different paths you can go in, that once again, you never be bored. Because boredom is the worst thing that could happen. Did I answer your question?
Yeah.
Okay. Any other questions? Okay. Well, thank you very much for coming.